It's Dave Odell again with Borie Davis Incorporated, located in Alpharetta, Georgia. We are your local HVAC ABB Drives representatives for the state of Georgia. And today we're providing you with the second in a series of videos. This video is variable frequency drive theory, simplified PWM, pulse width modulation. So in our last video we went through the mechanics and the math associated with how different loads work, the constant torque load and the variable torque load. And we saw that we could grab some significant energy savings if we could just move the prime mover and vary the speed of the prime mover. And we did, shared mechanically the value of that. Now we have to build the electrical product that will do that, and that's what we're going to talk about now. How does this box do it? Looking at this particular slide, I just want to share with you that we offer the drive different ways. This is a drive only, we call it. And this particular drive is UL type 1, meaning it's louvered. The air in the room it's located in will get into where the electronics are. So you want to make sure that's a clean environment. We'll talk about that more as we progress. This is a drive with some sort of a disconnect and fuses, either a disconnect or a circuit breaker and input fuses, so that you've got the one package there with what you need to provide the protection. This is a drive on top of a bypass package called the vertical eclipse package. This is UL type 1 only, so it should be in a clean air environment. But the drive is located on top of the bypass. Makes for a nice slim package. A lot of people like that. Covers are plastic or a composite. And then this is what we call the box style. The drive is located in this metal box, and the bypass is located in this metal box. So it's more of a box style offering. It's the same offering this, but box style, and this can be offered in a variety of enclosure styles: UL type 1, type 12, type 3R, and we'll talk about that as we progress also. Before we get into the technical side of the variable frequency drive, I just want to share with you the relationship between ABB, Borie Davis Incorporated, and the HVAC drives market. In 1981, a small drive manufacturer in Orange, Connecticut, developed and introduced a variable frequency drive specifically designed for the HVAC market applications. That company was Parametrics. Parametrics contracted with rep agencies across the United States and provided exclusive marketing territory for them. In the state of Georgia, they contracted with Borie Davis Incorporated in 1981, 42 years ago. In 1984, Parametrics was acquired by ACEA, a large European electrical company that dated back to the 1880s. In 1988, ACEA merged with Brown Boveri, another large European electrical company, and the company's name was termed ABB. In 1989, the factory in Connecticut was closed and full production began to occur in New Berlin, Wisconsin, a suburb of Milwaukee. It is there that the variable frequency drives for the Americas is manufactured even to this day. You can see from this slide the history of the HVAC drives manufactured by ABB. 6 generations over 42 years. Over those 42 years, Borie Davis Inc. has maintained the contract with ABB as their representative to the HVAC market in the state of Georgia. This has several benefits. ABB is the market leader by far in the HVAC market in the United States of America. Borie Davis has knowledge and hands-on history with every ABB variable frequency drive generation. Borie Davis has structured their relationship with ABB to provide more than just typical sales and product awareness. They've invested in technicians that have been factory trained and certified to perform authorized factory startup, to provide warranty service with factory reimbursement. We have 2 VFD specialists like myself who provide phone support to our customers, provide training on the product like this video we're doing. We do that in the field. We can do it in person. We do hourly presentations for engineering or for contractors or for customers, lunch and learn type visits. And we also have the ability to do harmonic analysis, software analysis of the harmonics in a building. And we have the hardware. We have power quality equipment to be able to offer an on-site harmonic study using the real system. Okay, so we have a plethora of services that we offer to the customer, and it's all by calling one number, calling one company, Borie Davis Incorporated. Now you'll note in the slide here those 6 generations. If you look close, you realize that the ACH580 is a drive offered from 2002 to 2023. That's 21 years. That drive, which is the predecessor to the ACH580, covers half of all the time ABB has a drive offering for the HVAC market. It was a workhorse, and as we're going to learn, the ACH580, all care was taken to make it as retrofittable into the physics and the electrical considerations associated with the 550 series. So ABB continues to provide products that are amicable to the customers, present, future, and the past. So what we're looking at here is a simplified power structure of a variable frequency drive. You can see on the left your power source, typically 230 or 460 volt, 60 hertz. The power generated down the line comes into the drive with a fixed voltage, fixed frequency, and the drive is going to convert all the incoming AC to DC across this bank of capacitors, and we've got some chokes in here to filter, and then we're going to manufacture AC, 3-phase AC, out to the motor. So we're going to have to create 3 phases, a positive and a negative alternation for each phase. So looking at our input, we're just looking at one phase here, but it is 60 hertz, and if you do the math on what frequency, 60 hertz is the time for one cycle of 60 hertz is equal to 1 divided by 60 hertz. And that works out to 16.6 milliseconds. So every 16.6 milliseconds, a cycle of input occurs. The positive alternation will be rectified by a pair of these diodes, and then the negative alternation will be rectified by a pair of these diodes, and it will, so that all three phases and all alternations of all three phases will be rectified and charge this bank of capacitors up. As long as power is applied to the drive, those capacitors will be charged. Okay. Now on the output, we've got to make variable voltage, variable frequency, because we said when we boiled everything down with the math earlier that a drive really is simply a volts per hertz device. So we're taking the 460 volt, 60 hertz motor data, and we're making a 7.66 volts per hertz device to create the proper output waveform of frequency and amplitude, and we'll see how that works as we move into these slides. When you check your incoming line voltage to make sure it's the correct voltage for the drive you've selected, you actually measure a volts RMS, root mean squared. And the voltage RMS that you measure, the root mean squared, is not the peak of this waveform. It is the root mean square value of the sine function. And that is less than the peak value. The actual peak value is equal to the RMS value divided by 0.707. Okay, that would give you the peak. Or you could take the reciprocal of 0.707 and the RMS would become RMS times 1.414 would become the peak. That means actually the 1.414 is the square root of 2. That's where that use come from with the root mean square, square root of 2. Hence, if you measure a 480 volt RMS line by this math, it would mean that the peak of that sine wave is actually 697 volts peak. The DC bus capacitors in the drive will attempt to charge to the peak of the incoming AC whenever and whilever power is applied to the input of the variable frequency drive. Okay. The input section, you may recall moments ago, consisted of 6 diodes. A diode is like a check valve in a fluid system. If you put the pressure on the diode in the correct polarity, it will break down and conduct for the entire alternation until the pressure is on the wrong direction. In this case, looking at this diode, if we apply this waveform of 460 volts, 60 hertz, this diode will begin to conduct when this sine wave goes above 0.8 volts negative to positive, if you believe electrons flow. So negative to positive at 0.8 volts, and remember this peak is 679 volts, so this thing is going to conduct on the entire positive alternation. But right here, which is this point here, the polarity reverses across this diode, and it does not conduct. So you see there's nothing going through the load on the negative alternation. Then on the positive alternation, well, it'll conduct again, and we'll see that waveform across the load. That's how a diode works. And of course, recall we have 6 diodes in the front end because we're doing full wave rectification of all 3 phases. So we would be producing these positive alternations, all 6 alternations, charging up the bank of capacitors continuously. As long as power is applied on a 480 volt line, they would be about 680 volts on the DC bus, and that will hurt you. It'll get your attention if you get across it. It may get too much attention, and it may complete your life for you, so you need to be careful around electricity. The midsection of this drive is the DC link reactors, and of course the DC bus capacitors right here. And some people, you can use DC link reactors, you can use AC line reactors, but on the smaller drives and older history, people didn't use any reactants in here because it costs money to put it in there. The ABB ACH580 unit uses 5% dual DC link reactors, meaning they're dual. One in the negative side of the DC bus, one in the positive side. The rated 5% would be basically 5% of the impedance of the motor. The smaller percentage, the smaller the effect they can produce for you. And their benefit is providing transient protection. And you may recall I stated that the DC bus is going to try and charge to the peak of the incoming line. Well, if our incoming line, the red wave is a perfect sine wave, but the reality is you start and stop equipment in the building. And if you started a large compressor, you might get a spike on the line. And that spike on that line, you can see there's the peak of the AC. Well, there's a new peak. And that caps, if you let the caps see that peak, they're going to try and charge to it. And the capacitors in the drive are the limiting component, concerns voltage. We mentioned that in the last video. But if you exceed the voltage rating of the capacitors, the blue smoke would come out and we're all done. So we have to have a overvoltage fault circuit to protect those capacitors, but that will shut down the system. Okay, so we just need to be aware of that. It's a protection for the bus caps, and that peak right there would cause that to trip, unless you have some form of impedance in the form of dual DC link reactors or AC line reactors. The impedance opposes a change in frequency across it. This is the equation for impedance in the inductors, these dual DC link chokes. Is 2 times pi, we've heard that before, FL, where F is frequency and L is the inductance. Well, a spike is a high frequency component, so as this frequency goes up, this impedance to that spike goes up, so that it will clip the spike, so that if a surge comes along, these being in front of the bus caps will clip off that spike if it's short duration, so that the bus never sees it, never tries to charge to it We never have to shut the system down. It's amazing how well they work and how little they cost, but some manufacturers for a long time did not consider this valued. ABB's been putting these impedance in the form of dual DC link chokes in front of the DC bus since the early 90s. They also filter the rectified AC to give us a nice smooth DC to work with. They also reduce harmonics, which is a very important subject that can affect other equipments in the building, and that's really a separate subject that you can call us and talk to us on, or maybe we'll do a video on at some point. But I don't want to take up all your time. That subject takes at least an hour to talk about properly. But the fact that an impedance is put in there in the front end is helpful to reducing the harmonics that would be placed back on the line. Okay. Yes, and the bottom line here is VFDs that are offered without a reactor in them often trip on overvoltage because of what I just shared with you up here. Now I've taken the top off an ACH580 here, and if you take the cooling fan off the top, there's the dual DC link reactors right there. And then I took a drive apart, and if I took this top off, this is what I'd see. There are the dual DC link reactors. This is looking down from the top down. This is it all stripped away up top, and you can see them. They're not small. They're significant. So it's important that you don't let somebody try and tell you this thing the size of my thumbnail is a DC link reactor. That's not true. Okay, they're like a little control power transformer. It's a bunch of wire. It's inductance to help again reduce and provide additional transient protection and harmonic reduction. Okay. Having converted all the incoming line to DC, we now are tasked with making variable voltage, variable frequency out, and it's got to drive a three-phase AC motor. That's what we drive, three-phase AC motors. So the basics of driving a three-phase AC motor, the requirements are, one, you've got to have three phases. You got to have a phase 1, phase 2, phase 3 here. Each phase has to have a positive alternation and a negative alternation. Okay? And from phase 1 to phase 2, you need a phase shift of 120 degrees. Phase 2 to phase 3, another 120. And phase 1 to phase 3, we need to repeat every 360 degrees is when we start to cycle over again. Okay? So 360 degrees, again, your complete circle. Okay? So that's what we have to make in order, that's what three-phase AC is, so that's what we have to make. We have to make three phases. We have to have a positive and negative alternation for each, and they have to be phase shifted 120 degrees. And the fact is, this horizontal axis is time. The vertical axis is the amplitude of the voltage at that moment in time. To manufacture the voltage and frequency leaving the drive, we're going to be using a device called an IGBT. It's an insulated gate bipolar transistor. It's a mouthful, but in reality, it's not as difficult as it seems. It's actually reasonable because it's telling you uh, it's a bipolar switch, just like a light switch. It's either on or it's off. Okay, that's the only two states it operates in. It's bipolar. It's either on or it's off. So light bulb on, light bulb off, vice versa. But to turn it on and off, there's a gate signal. And the gate, if you look here, there's no connection between the gate and the collector emitter junction of the transistor, the IGBT. It's insulated, which is what the IG is, insulated gate, bipolar transistor. And what happens and how it works is if transistors are doped with P or N, positive or negative type materials. And so normally this transistor is sitting here, and if this is negative, then this is more negative, meaning it's not going to conduct. And if we come in here with a gate signal, and if the gate goes positive, and this little positive, this may be 5 volts, okay? But if that goes positive 5 volts, that produces an electric field from the gate. And that field breaks down this, it dopes this material with a conducting values, which allows this transistor to conduct. And one side of this transistor is tied to the DC bus, the other side's tied to the motor, okay? So if this switch is on because the gate is on, a field is generated and the DC bus is connected to the motor. If the field or the gate goes to 0, this field collapses and the DC bus is no longer connected to the motor. Okay, so it works just like a light bulb. Okay, except the exception is this IGBTs. Here they are. There's 6 of them. There's 3 tied to the positive side of the DC bus. There's 3 tied to the negative side of the DC bus. We need 6 because we got to have a positive alternation, we got to have a negative alternation, and we got to have 3 phases. Okay? This IGBT can be turned on and off up to 20,000 times per second. That is quick. And that is what we're going to use to create the voltage and frequency of the output. Now, again, I've told you before, this is pretty much PWM is how everybody's VFD works. They're volts per hertz devices. So this is how everybody's doing it. Obviously, we'd like you to only use ABB, but this is how they do it, okay? You come in with this 460 volts, 60 hertz. The diodes rectify all the incoming AC and charge up a bank of capacitors, and the dual DC link reactors filter it out and reduce the harmonics put on the line and provide us some transient protection. But then we take the DC bus, and for the positive alternation, we turn the positive switch of a phase on to put that side of the bus at the motor. And the negative side of the switch we could turn on when we turn off the positive side, turn the negative side, send him out to the motor. Okay? And we go back and forth, and that's the frequency right there, how rapidly I turn these on and off. The voltage is going to be a little more difficult, so we're going to use more slides to show you how we do voltage. Okay, but this is the basics of what we're going to be doing. What I've done here is provided us some pictures. I want you to know inside the drive itself, this this little package has the IGBTs and the diodes in it. They're all in this one package. So these 6 IGBTs and these 6 diodes are sitting inside this little package. It's amazing how compact and yet powerful variable frequency drives have become. This package is this section right here on this drive. I just took a drive apart and wanted to show it to you. But there's the IGBTs. Down here are the input terminals, where you tie in the input, the 460 coming in, and over on the right over here are the output terminals. Now, as I showed you in a different picture, here's the DC bus chokes, and they're in both positive and negative. There they are physically. They sit down in the cooling channel. And then over here, these are the bus caps. Okay, so they're in the cooling channel also, which is actually outside the electronics. Okay, and here's the heat sink. Okay, so a lot of thin surface area for the heat to transfer out into this cooling channel. And in this channel, the fan sits up on the top of this channel, just like I showed you in the pictures before. Okay, and right on the back side of this heat sink, that's what that is. That's sitting, this is the front of this board, this is the back side. Okay, so that's what the drive looks like, that's what all the power components look like, and that's how you tie it in and out. Okay. First thing to do, we're going to create the frequency here, so we're going to show that piece first. And frequency in hertz is equal to 1 divided by time, or time is equal to 1 divided by frequency. So if I want to run at 1 hertz, 1 cycle per second, then 1 divided by 1, that would be 1 second per cycle. So from the time I go positive to negative to start over again would be 1 second. That's 1 hertz. I run 2 cycles per second. That would be a half a second per cycle. Well, that would mean I begin to repeat every half a second. That's 0.25 seconds for the positive alternation, 0.25 for the negative. Okay? 5 cycles per second, 5 hertz. That's 1 divided by 5. That'd be 0.2 seconds per cycle. So positive alternation, negative alternation, every 0.2 seconds. A half cycle would be 0.1 seconds and 0.1 seconds. Pick a number. Divided by 1, you get the time for that cycle. To make 3-phase AC, again, we have to have 3 phases. Phase 1, phase 2, phase 3. Each phase has to have a positive alternation and a negative alternation. And there should be 120 degrees phase shift between phases. And that phase shift is phases in time. So here we are with the first, I want to run 1 hertz. That would mean this waveform repeat every 1 second. That means the positive alternation should be on for half a second, the negative. So positive side of the DC bus is tied here. If I turn this switch on for half a second, then the DC bus positive side is here at the motor. If after half a second I turn the positive side off and immediately turn the negative side on, then on the same phase, then the negative side of the bus is felt at the motor. If I go a half a second and then shut that device off and turn the positive back on, you see if I keep going back and forth, I'm producing a frequency of 1 hertz to the motor. Let's try 2 hertz. Well, 2 hertz would be half a second per whole cycle. that would be 0.25 seconds per alternation. So yeah, I turn this switch on for 0.25 seconds, and as long as it's on, that positive DC bus is at the motor. I shut that off and immediately turn the negative on for 0.25 seconds. The negative side's at the motor. And if I repeat and repeat and repeat, I'm running at 2 hertz. Pick a number. You want to run 60 hertz? Well, 1 divided by 60 is 16.66 milliseconds, meaning this waveform repeats from here to here every 16.6 milliseconds. That means one alternation is 8.33 milliseconds, then make a negative alternation for the same time. So I turn this switch on for 8.33 milliseconds. That puts the DC bus at the motor for that time. I immediately shut that off and immediately turn on A0, your A negative. The negative side of the bus is out at the motor for 8.33 milliseconds. I keep doing that, and I've got myself 60 hertz waveform. Now, there has to be 120 degrees in time phase shift. So this is one phase, but what about phase B? Well, phase B needs to be shifted in time 120 degrees from phase A to B. Well, if I'm running at 1 cycle per second, that means this is 1 second. What is 120 degrees out of this full 360? Well, 120 degrees is 1/3 of 360. So 1/3 of 1 second would be 0.33 seconds. So 0.33 seconds after I fire phase A, I would fire phase B and do the same thing to B. And then 0.33 seconds, or 1/3 of the period time of the frequency, I would then fire phase C. And so you create the one signal you want, what frequency I want to run at, and the microprocessor easily calculates based on that. Well, that means it occurs every how many seconds or milliseconds. Well, take 120 or 1/3 of that time, and that's the time between phases, and you take the one signal based on your 0 to 10 volt input, and that creates 0 to 60 hertz and sets everybody up for when they should fire on time from that one signal. And that's how we do variable frequency, and I hope you saw that in this. In these next few slides, we're going to show you the frequency we've developed. This particular slide shows that we have a horizontal axis relative to time with a maximum shown of 1 hertz or 1 second per cycle. Now, but what's actually shown here is a waveform that's 2 cycles in duration over 1 second, and each cycle takes 0.5 seconds. Well, frequency is 1 divided by time, or time is 1 divided by frequency. Well, if the time is half a second, well, 1 divided by half a second is 2 hertz. This waveform is a 2 hertz waveform. It repeats every half a second, and within that there's a 1/4 of a second positive alternation and a 1/4 of a second negative alternation, because that's what's proper for AC, a positive and a negative, and the frequency is dictated by how long does one cycle take. This waveform is on the same horizontal axis, the same duration. It's a 1 second axis, and you can see that in this case, one cycle is only taking a 1/4 of a second. Well, if 1 divided by 0.25 seconds per cycle, that tells me That's a 4 hertz waveform. Still need a positive and a negative alternation, but that's what you see there. Okay, so this is a 4 hertz waveform. You also notice relative to each previous one and ones that follow, the distance here, this red waveform seems to get tighter or spread out based on lower frequencies. These spread out more. Higher frequencies, you're going to see these will condense. That's important to realize as well. This waveform is a 15 hertz waveform. I know that because one cycle occurs in 66 milliseconds, and if I take 1 divided by 66 milliseconds, you're going to come out with 15 as the value. So 15 hertz is what this waveform is, and you can also see relative to the 4 hertz waveform we had, these red things are getting closer and closer. They're getting more compact. Okay. Now this waveform is even more compact. It's repeating itself at every 33 milliseconds. Every 33 milliseconds. So 1 divided by 33 milliseconds is 30 hertz. So this is a 30 hertz waveform, and you see those red lines there. They're getting even more compact relative to the lower frequencies we've been making. This is a 60 hertz waveform. You see that one cycle occurs every 16.6 milliseconds. And if you divide 1 by 16.6 milliseconds, you're going to get 60 hertz. That's what this waveform is. You see 2 cycles are shown. In every one of these last slides, I've only shown 2 cycles. And as you can see, the time base has always been 1 second here. Well, you can see how this frequency waveform is being more of them are occurring in the same given time. 60 of these would occur over this 1 second. They'd fit in that time period. This is the way power is generated in the United States, 60 cycles per second. We talked about that in the last video. So that's that, and the red you can see is really getting compacted up here, and there's a reason for that we'll talk about. Now that we've determined how we make the frequency to the motor by simply turning on and off the IGBTs, now we need to be able to make the voltage to the motor also. And so what we're showing here is basically the fact that all we have available to output is the DC bus, either in the a positive 650 volts or at 0. And my statement to you is if I turned this gate switch on at the frequency I want to run at, then as long as it was on, whatever's on the DC bus would pass through to the motor winding. We only have 650 volts to send, and you can imagine, hopefully, if I just turned this switch on and kept it on all the time, I just fed it 5 volts, which turned it on, it was on all the time, then I would be sending all the DC to the motor. Okay? Can you see that? This would be a solid line, meaning everything that I had on the DC bus was going to the motor. On the opposite side, if I just sent a 0 signal to this gate, this switch would never turn on, and I would have 0 volts on the motor all the time. Well, we're doing something in between there. It's almost like we're doing a duty cycle, some on time versus off time. So if I have this bus, and let's say I have the ability, and I actually do, turn this switch on and off 1,000 times a second. So that's called the switching frequency. Well, a 1,000 hertz switching frequency, if you divide 1 by 1,000, means that a cycle occurs every millisecond. So every millisecond, that pulse train repeats itself. But during that 1 millisecond, we're going to control the duty cycle, which is the on time versus the off time. So in this first example, we have the DC bus is switched off and left off for 0.8 milliseconds out of every 1 millisecond, and it's on for only 0.2 milliseconds. So 20% of the time, the DC bus is applied to the motor. Well, over time, we're saying, would that not mean that the motor is seeing 20% of that waveform, 20% of that amplitude, i.e., if we added all these pulses up, they'd fit under here, this would be solid under here at 20%. And it makes sense, okay, because it's on 20% of the time, and that's 20% that the DC bus is being pulsed out there. In the second statement, we just flip the duty cycle, and rather be on for 0.2 and off for 0.8 milliseconds, we're saying for every 1 millisecond cycle, we're going to be on for 0.8 milliseconds and off for 0.2. Well, just look at it. We're off periods is skinny section, and the on periods is thick section. Well, that's a lot more of the DC bus going to the motor than is not going to the motor. Matter of fact, if I added all that up and was to make a rectangle out of it, it would fall under the 80% of the DC bus being sent to the motor average all the time. If you can see that, that's how we're going to vary the voltage to the motor, by varying the duty cycle on what's called the switching frequency. Now the switching frequency, just to be honest with you, because it's a little confusing, that is turning how rapidly I turn it on and off an individual IGBT. This is just like, this is the positive IGBT for an alternation, and I hit it with a signal like that. And then if I'm operating at 1 cycle per second, this is on for half a second, but I've hit it with this signal 1,000 times in that half a second. Okay? Then I shut him off, and I go do the same thing to the negative IGBT. And that's how we're going to establish the voltage and the frequency. Now it's called pulse width modulation, PWM. And it's because it's trying to describe how we're going to produce this voltage. Well, the microprocessor in the drive knows what a perfect sine wave looks like. It's the blue dotted line here. That's the perfect sine wave. First thing we'll notice about this particular sine wave, it repeats itself every 20 milliseconds. If you divide 1 by 20 milliseconds, you're going to realize that's a 50 hertz waveform, 50 cycles per second. Okay? And if we're a 60 hertz, 460 volt motor running at 50 hertz, well, 50 divided by 60 we should be at 83% speed and 83% voltage for a constant torque load, right? Volts per hertz should be constant, so we should be at 382.63 volts due to maintaining constant volts per hertz. Well, the microprocessor and the drives know that this would be the perfect waveform in amplitude and duration of a 460 volt 60 hertz motor running at 50 hertz. The blue dotted line representing that sine wave, the reason it's dotted is because it's not the line that sends the energy to the motor. It's the information below the line. The dots represent at any moment in time what the amplitude of the voltage sent to the motor should be from 0 to 360 degrees. Okay? 0 to 360 degrees, that's a complete cycle. Okay? Well, the microprocessor in the drive knows it does not have a sine wave that it can send. But it does know that if we look at 1 millisecond into this 20 millisecond waveform, we should have sent this much information, this mass of energy to the motor. Well, we don't have that mass to send. All we've got is this DC bus. So if I turn that positive IGBT on for that amount of time, then this fixed height times that width will equal the same mass of energy that would fit under this section of the sine wave. And then it waits and it evaluates, okay, at 2 milliseconds, I should have sent this mass of energy to the motor, what sits between the blue dotted line and 0. And said, well, I don't have that mass to send, but I can send this 650 volt bus, and if I pulse the same IGBT on, but leave them on a little longer, then this height times this width will equal that same mass under that section of a perfect sine wave. And I'm not going to go through all of them, but you can see as we move toward the peak of this sine wave, these pulses on the same IGBT get wider and wider because I'm trying to recreate the largest pieces of mass at the proper time in the sine wave. And then on the trailing edge, you see the pulses trail off because we're trying to create smaller masses that would be on the trailing edge. Now, right here at 10 milliseconds, I'm done making the positive alternation of 50 hertz, 400 or 382 volt waveform. And I now shut off the positive IGBT and go do the same thing on the negative IGBT for that phase. And that's how I do the frequency and the voltage. Pulse width modulation is trying to share with you how we create the right amount of energy in the right amount of area of a perfect sine wave. But it's actually DC that we're pulsing. It's the DC bus, okay? And the motor filters that out. The motor believes it's AC and filters out the frequency content. Sometimes you hear this switching frequency in the motor, and we'll talk about that a little later, about the considerations of that. But the fact is, this red waveform is the phase to ground, if you put an oscilloscope on the output of the drive on each phase to ground, that's what you'd see, that red waveform, okay? And the motor filters it out. Now, if you looked phase to phase, this is what it would look like with an oscilloscope phase to phase, because the two phases are adding like they were earlier when we had the sine waves up there. For any two phases, they are additive. When you put all three together, they should all three at the same time equal 0. But I think you can see here that there's no way we're going to get 0 again here. Okay? But I want you also to see with this waveform of 50 hertz that from time 0, if this is the phase A, then, and it repeats every 20 milliseconds, okay, which it does for the same place in the waveform, then if this is phase A, phase B should be fired 120 degrees later. Well, 120 degrees is 1/3 of the cycle time. And if the cycle time is 20 milliseconds, well, that means at 6.6666 milliseconds, phase B should fire their IGBTs. And then another 6.66 milliseconds, so somewhere around 13, phase C should fire. And everything's tied into just the firing signal of the first phase, and then everything is done by the time base for the frequency. So all we have to do is know what frequency we want to run at, and all that is gotten from a 0 to 10 volt signal or a 4 to 20 milliamp signal telling me what speed we want to run at. And with that signal, we can create the voltage and frequency that keeps the motor happy. And as we shared in the math with the mechanics and the electrical, everything is happy. And we get a long life and we get the greatest energy savings out of the system. So that's the power structure of anybody's variable frequency drive. That's how they function. Now, the key for you people that do the servicing troubleshooting to remember, one reason I put this slide back up, is to remember the input voltage is fixed voltage, fixed frequency. The output is variable voltage, variable frequency based on 460 divided by 60 or 230 divided by 60. So the ampere readings and the voltage reading are going to be a little different from input to output, and I just want you to be aware of them. Recalling that horsepower equals volts times amps times efficiency times power factor times the square root of 3 divided by 746 watts per horsepower, and all these things in red are basically fixed, constant. You need to just be aware. Horsepower is volts times amps is what it boils down to in general. So we have input volts and we have input amps. We have output volts and we have output amps. And for a given 5 horse, 6.7 amp, 460 volt, 3-phase, 60 hertz, 1760 RPM motor that's been properly designed by the engineer for the application, at 25% speed with a full load on the motor, 6.7 amps on the output, we will only be at 115 volts. If we're at 25% speed, we're going to be a maximum of 25% voltage. 25% of 460 is 115. Now, so it'll read like we're fully loaded on the output amps. But on the input, that's what you pay for electrically, which is fixed at 460. The input amps for that given load, 770.5 basic power output, and you'll have the same on the input, but because we're at 460 fixed, the amps will be 1.675. Now you can pick another speed, and you see on the input the amps go up, the voltage is fixed because it is. That's what Georgia Power supplies, on your utility transformer in the building. But the output voltage varies, and the amps on the output remain relatively fixed. Okay? But in each case, the same amount of power required is being delivered. Okay? Right? You pay for input amps. You're not really, don't look and say, oh, it's 6.7 amps fully loaded all the time. No. The power required is the amps and the volts. Okay? And if I ask you, if you're troubleshooting, I'll ask you to go measure all three phases of input amps. Run at some speed and measure them. I'm looking to see, are they balanced? And then I would ask you to look at the output amps, see if they're balanced. But I would not expect the output amps to equal the input amps at all. Okay? Because unless it's 60 hertz, then you might be close. Because that's when everybody's at 460 volts, 60 hertz. If you're fully loaded, you'd be 6.7 amps. But other than that, I don't expect the input amps to be relative to the output amps, but I do expect the input amps phase A to equal phase B to equal phase C, and the output amps phase A to equal phase B to equal phase C. Anything other than that indicates I have an imbalance, and we need to find out where that's coming from, because that can cause an issue, which we'll talk about when we get into troubleshooting and maintenance. This concludes the video on variable frequency drive PWM theory, and just want to share again, we are Borie Davis, the exclusive ABB HVAC rep in Georgia. There's our address, phone number, website. Don't hesitate to give us a call if you have any questions. A couple more slides to follow that are basically advertising for us. Thank you for your time. The next video will be out shortly. Borie Davis is proud to offer full service capability on all VFDs. We have the certifications for ABB on startup and warranty service, but we service other people's VFDs too. We're not authorized, but anything out of warranty. If you got people that have basically been in the business 42 years, we come across a lot of drives. So this is our service team, and Monty Monterdi is the service manager. He's a hands-on man. He's our licensed electrician. And then we have service technicians here. Those guys are out on the road all the time, providing training, warranty service, certification that they do, that they are certified on the drives. We have several videos on the ACH580 on our YouTube channel for your viewing that share many programming items associated with the drive. Please enjoy them. This is the YouTube site, or you could just Google Borie Davis YouTube videos and it would take you there. And with any questions that come up, don't hesitate to contact us with anything that arises out of this presentation, or any questions you have that you've just been thinking about and wondering a long time. Could be that we can answer them, and we'd be happy to. Our VFD specialists are one, myself, and two, Brad Templeton. Myself, I worked for that little company in Connecticut back in 1978 and left it in '84 to come down here and be their territory manager from '84 to 2011, and then I went to work for Borie Davis as a VFD specialist from 2011 to present. So I've got a history that dates back now too many years to remember, 45 years, I guess, um, in the business with ABB in one name or another in their variable frequency drives group. Brad Templeton, our other specialist, he came to us from an industrial ABB distributor, and prior to that, he worked with Baldor, their regional motors group right here in Alpharetta, Georgia as well. So he has a wealth of knowledge on drives and motors. Of course, I don't know if I've mentioned it yet, but ABB, when they back in 2009, they actually bought Baldor, and so Baldor is part of an ABB group now. So they're both. If you're using Baldor motors, you're using an ABB motor now. And as a matter of fact, our ACH580 drive, the default motor parameters in the drive as shipped from the factory match the 4-pole base speed 1800 RPM Baldor Super E HVAC motor. So, and we are a distributor rep for those people too, for the Baldor motors. So we'd be happy to entertain any information you need on those as well. Thank you for your time today.